Motors with steel rotors are purely magnetic machines because they don't depend for their action on any electric current flowing in the moving part. Unlike, for example, this copper cylinder. And when that spins, it does so because an electric current is caused to flow in the copper. And so I call this an electromagnetic machine. Now, by far the most intriguing magnetic machine for me can be made simply with an ordinary paperclip. First, I unroll it, and then wrap it around a pencil or other non-conducting rod, and then offer it to the linear motor. So this spins very well, as you see, and yet there is clearly no electric circuit, so no current can flow in the clip. Now I want to distinguish very clearly between magnetic machines and electromagnetic machines. Both types are used extensively, both in industry and in the home. A washing machine, for example, uses an induction motor, which is an electromagnetic machine. Electric clocks, as we've just seen, are magnetic machines. Now, magnetic machines get better as they are made smaller, whereas electromagnetic machines are better as they are made bigger. This last fact I can prove to you in more general terms by using what I call my goodness models. Now, every machine has a magnetic circuit, which I represent like this. The flux in that circuit is made to induce a current into an electric circuit, which links it, like that. The force you can get from a machine is proportional only to the product of the flux in the magnetic circuit and the current in the electric circuit. So flux and current are the things you want lots of. The thing which stops you having as much as you like, of course, is the resistance in the case of the electric circuit, and the magnetic resistance, or reluctance as we call it, in the magnetic circuit. The resistance of an electric circuit is proportional to its length, and inversely proportional to its area. So if I take a second electric circuit, which is twice as big in every linear dimension as the first, then its length will be twice as great, but its area is 4 times as great. So the resistance of the big circuit altogether is only half the resistance of the small circuit. And when we put the two circuits together to make our machine, the combined effect of the two is to make the big machine 4 times as good as the small one. So it seems as if the rule for electromagnetic machines is that the bigger they are, the better they are. Now with purely magnetic motors, the rules seem to work the other way around. Let me show you what I mean. These sheets are made of rubber, but it's rubber which has been impregnated with a magnetic material, and they've been magnetized, so that the whole of that surface is a north pole, and the whole of that is a south. And yet, there doesn't seem to be any measurable force between them. They behave as if they were unmagnetized. But if I take some scissors and cut 2 pieces from one of the sheets, then we see how those behave. There's no noticeable repulsion, but at least there's some attraction. And if I cut smaller pieces still, then at once there's attraction, and this time there's even some repulsion. Put one piece on top of the other with reverse polarity, and it just doesn't want to know the other one. So magnetic things get better the smaller they are. Now let's apply this principle of size to our fascinating